All right. Well, hello there. So it's been brought to my attention that you guys don't have a good video for probability parts for calculus. So let's go ahead and make a video talking about probability in calculus. So we have that. All right. So the things that we want to deal with, just kind of discuss this thing. So a probability density function. So in a continuous probability distribution. Okay, we have the idea of a probability density function is that the f of x is going to be greater than or equal to 0 for all of its domain that we care about. Okay, so all where it's defined, it's going to be greater than or equal to 0. And here's the thing about the probability is that the sum, like if we were doing discrete probability, not continuous, discrete, we would say the sum of all the f of x's have to add up to 1. Well, you don't have that in continuous distribution, right? You can't just start adding up little bits and pieces. So instead of a sum, we say we have to integrate all of the f of x that has to equal to 1. So that's what the two conditions for something to being a probability density function are. It's like, well, the integral has to be 1 and the function has to be positive everywhere. Okay, so those are the two things that we're going to go with. We're going to say that the probability between like 2 points, probability of x and b, and that's going to be, again, integral from a to b of f of x dx, and we just go ahead and integrate that out. Okay, so that's how that's going to work there. Things that a probability distribution does not have to be: probability density function, probability distribution being kind of synonymous here. It does not have to be a differentiable function, so we could go ahead and come up with a function that looks something like this, right? Just we'll put an open dot here, closed dot, open dot, closed dot. So clearly not something that's not something that's differentiable. But if all of these areas add up to 1, then it would be a probability density function would be okay. So we have that all of that. So that's the thing to remember is like it doesn't have to be differentiable, but it does have to be the area has to be equal to 1. Okay, so it doesn't have to be integratable. All right, so you have a couple of different flavors of problems in this section. One flavor is the kind of problem that I like to ask you, and that's things like if I give you a function, prove that it's a probability density function, I prove that it integrates out to 1, and then you can kind of do a quick sketch to make sure that it's always greater than 0, kind of an idea. Okay, you guys don't have graphic calculators, so if that's I can't give you one that's too tricky because I don't want to have you figure out like, well, it doesn't equal to 0, does it go under, that kind of an idea. Okay, and then figuring out different probabilities and things like that. So we could do that. Okay, so one of the examples, I'll use the example that they have in the book and say, okay, well, f of x equals, and they're almost always piecewise functions. Okay, so we're going to go ahead and say this is a 0 point. What do I have here? 1, 2, 6, and x. And then I have a 10 minus x. And this is for when x is somewhere between 0 and 10, and 0 otherwise. Okay, so if I wanted to go ahead and graph this real quick, right, this is a parabola. It's got zeros at x equals 0. It's got a 0 at x equals 10. Other than that, it does face down. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we are having a parabola, something that looks like that. So we are above the axis. We will check in a moment to see, is this going to integrate out to 10? So we can always check. It's like, well, does it? So we could say integral of 0.006 x. Actually, I'm going to do it this way. I'm just going to add them up together. There's excuse me, there's like 7 ways from Sunday. You can choose to do this. So I went, okay, what do I have here? 0.06. Yeah, I said 0.06x minus, and then 0.006 x squared. And I'm just going to say, okay, we're going to go from 0 to 10 dx, and we're just going to check, does this thing integrate out to 1? Okay, that's all we're going to do here. So not so bad. And again, you could have factored that constant out first. That would have been fine. But let's see here. We are going to end up with 0.06 x squared over 2 minus 0.006 x to the 3 over 3. And we're going to check between 0 and 10, dot, dot, dot. And then we'll go ahead and do our arithmetic here. So we get, what, 0.03 x squared minus, and this is 0.002 x to the 3. Okay, and then we're just going to plug in our 0 to 10 and see what happens, and plug those things in. If I plug in 10 here, right, I get 0.03 times 10 squared. This is going to turn out to be, 3. And then minus 0.002 times 10 cubed. That's going to be 1,000 times 0.002. And we end up with minus 2. 3 minus 2. Last time I checked, that's 1. So we integrate out to 1. We know that the function is always greater than 0. So check, it is indeed a probability distribution function. Great. Okay. So that's one kind of flavor of problem. And to be perfectly honest, I kind of like those. Okay. So I like the problems where it's like, here, figure out something to do to make this a probability distribution. There's like a sub flavor for this one. It's like, okay, if we have, say, f of x equals like c, I could have done it this way. We could say, go back up to what we have here, c x 10 minus x. And again, from x goes from 0 to 10. And it says find c such that f of x is a probability distribution. Okay, so that's one of the things we can do. So we integrate this thing out from 0 to 10. We would go ahead and deal with this, and then we'd still have the c out in the end, set it equal to 1, and then solve for c, and then we're going to get 0.006. Okay, so that's how they would do that. Okay, but that's I always like those kind of problems. They're kind of nice and pretty straightforward, especially considering the fact that the last couple of sections they've been really tough. So one of the reasons I like this is it kind of gives you at least a section to kind of catch your breath to say, okay, well, I don't have to be worried constantly about doing everything with all the really hard integrals that we've been dealing with. This one is a little bit tamer. This section is a little bit tamer. And we can go ahead and take a little bit of a breath. So we could do something like that. The next type of problem, so just to review, we have one flavor, check to see if a function is a distribution or force it to be a distribution. So we could say check if f of x is a distribution, or find c times f of x to make it a distribution, to make c times f of x a distribution. Okay, so those are two good types of problems to deal with. Okay, the next topic that we talk about is something called expected value. Okay, so what the idea for expected value is. Okay, so the definition for this thing is the sum of the value of the event times the probability of that event. Okay, we abbreviate it with EX. Okay, that's expected value. In terms of calculus, oh, actually, let me go back. In terms of what if we weren't having continuous distributions, we would write this as the sum of x times f of x over all of the x's over all the x's where this actually has a value. Okay, so that would be the expected value for this thing. In calculus language, this is also equal to the integral of x times f of x. Okay, again, over the whole domain for x. Okay, we'll call it negative infinity to positive infinity, but it will often be between an a and a b. And again, this is why this comes after your improper integrals, is so that you are able to properly deal with the fact that you might have some limits that go to infinity, something like that. Okay, so that's called expected value. Now, expected value is also the mean. Okay, so expected value. Okay, so I would when I teach statistics, I tell the students, like, expected is a vocabulary word now. Okay, when we say expected in statistics, we say expected when it relates to probability. It doesn't mean like what you think expected is. It's not the English term anymore. It means do this. Okay, that's what expected is going to tell you to do. It's either this one or that one. Okay, this is also the mean. So the expected value is the mean, which in statistics we will go ahead and abbreviate with this. This is mu. So we do it that way instead. Okay, so that's the Greek letter mu, and that's what we use for mean. I don't think our book goes off to tell us to figure out standard deviation or any of the other larger things that we have to figure out later than that. So just to give you a sense of the pattern, nobody's going to ask you this for a very long time. E of x equals the integral of x times f of x dx, again, over its whole domain, which is usually not going to be all of negative infinity to positive infinity, but you know what I mean. E of x squared is the integral of x squared times f of x from negative infinity to positive infinity. This isn't standard deviation, but you need to get this in order to figure out standard deviation. We're not going to worry about that for now. Just to show you the pattern, E of x3, again, I think you're kind of sensing a pattern as we speak right here, right? And then we have x3, f of x. This is related to skew. They do not ask you what skew is, and there's more that go up. Like x to the fourth is called kurtosis. That has nothing to do with bad breath. It has to do with the shape of the distribution. So we're going to go with that. Okay. So they could figure out the mean from this. Okay, and yeah, that's a thing that we could ask you, is like, hey, could you figure out the mean of this probability distribution, this probability density function? Okay, again, I'm using those words kind of synonymously. One of the more interesting problems for this one is something called the Cauchy distribution. Okay, so I have a pen here. So there's and they use this quite often. Okay, so Cauchy distribution, which I believe is 1 over pi times 1 over 1 plus x squared. The book likes this distribution. Okay, 1 over 1 plus x squared, 1 over pi. So the shape of this thing, it looks something like this. It kind of looks like a normal distribution, but the tails are a bit bigger than a normal distribution. These are thicker tails. So we can go ahead and figure out, well, is this a distribution? Like, how do I know? Okay, so let's go ahead and integrate this thing out. So we're going to integrate negative infinity to positive infinity from 1 over 1 plus x squared dx. And we're going to say, okay, well, we can't quite do that because we've got infinities in my integral. We don't want to do that. So I'm going to say this is 1 over pi. So I have a 1 over pi. I have a limit as, say, a goes to infinity, limit b goes to negative infinity, And then we're going to have for 0 to a of 1 over 1 plus x squared plus integral from b up to 0 of 1 over 1 plus x squared. Again, dx, dx. Okay, and we'll just go ahead and integrate that out. This one's pretty well known as inverse tangent, so we'll go ahead and say that, so not logarithm, not yet. So we're going to have inverse tangents. We have 1 over pi, and I've got inverse tangent. Actually, let me go back and be more careful about that. That is the whole point of all of this, is that we learn how to write it properly in this class. That's what we're doing. So I have the limit as a goes off to infinity, and I have inverse tangent here of x from 0 off to a plus inverse tangent there we go, plus inverse tangent or limit as b goes off to negative infinity for inverse tangent of b up to 0. Okay, and then we're going to go ahead and plug in our limits and see what happens. So we have 1 for pi. Here we have inverse tangent of a minus inverse tangent of 0 plus, and we'll still have that 1 over pi here, and we have inverse tangent of 0 minus inverse tangent of b. Okay, again, limit as b goes off to infinity from up here. Okay, and we'll go ahead and evaluate those. So limit as a goes off to infinity for inverse tangent is going to be pi over 2. Okay, at 0, it's just 0. Okay, remember we have a 1 over pi out here. Plus, we still have a 1 over pi. Okay, and then we have our 0 minus, as b goes off to negative infinity, we have negative pi over 2, right? We have negative. So we're going to have that. So really what it comes down to is we have 1 over pi. I'm going to factor that out, both of these terms. We have pi over 2 plus pi over 2. And pi over 2 plus pi over 2 will just be pi, and we'll have 1 over pi times pi. These cancel. Yay, we get 1. Not pi, we just get 1. So it is the probability distribution, so that's always good. The fun thing about this particular distribution is if I wanted to compute the expected value. Okay, so this is going to be x over x squared plus 1. There's a 1 over pi out in front. And I want to compute the expected value, so we're going to go from negative infinity to positive infinity. We'll hold off on the limits for just a moment because they'll get a little bit tedious to write. And we'll say, okay, this is going to be 1 over pi. We'll just treat this as an improper integral for the moment. And we'll say, let u equals x squared plus 1. du is equal to 2x. So what I'm going to do is I'm going to multiply a 2 here, but I can't just go around multiplying things by 2. We're going to balance it by multiplying by a 1/2. Here's my 2x dx. I'm going to substitute this 2x dx with a du, and then divided by, use x squared on plus 1 on the bottom. It's just going to be there. We have a 1 over 2 pi out in front from this bit here. Okay, from this guy's out here. And we'll just go ahead and integrate that, and we end up with 1 over 2 pi. There we go. 1 over 2 pi. And I just have a natural log of u. And we know that we're going to be dealing with an a to b here in a moment, but those are going to be improper, so we're going to have to do something about that. When I go ahead and plug in back my u, we have 1 over 2 pi. We have natural log of, right, x squared plus 1. You don't really need the absolute values at this point because x squared plus 1 is always a positive number, so we can just use parentheses instead of absolute value if that's preferred. And I think that's a little bit less intimidating, so let's go ahead and and go ahead and replace those absolute values with just parentheses. And again, we're going to go from an A to a B. Okay, now we got to figure out what the limits are. So we're going to say, okay, this is going to be 1 over 2 pi. We'll say limit as b goes off to infinity. Okay, and then we'll have natural log of x squared plus 1 from 0 to b. Okay, and then on the other side, we'll say limit as a goes off to negative infinity. And then we have ln of x squared plus 1 from a up to 0. Okay, and we can go ahead and evaluate those limits. So we'll go ahead and do that. We'll say we have 1 over 2 pi. That's delightful. And then I have got ln, well, we could switch over a limit, don't we? So it does get a little tedious to keep writing all of this stuff out. I get it, but this is the class where you're supposed to be learning to do this. So we have the limit as b goes off to infinity. By the way, don't forget that you still have limits that go off to infinity, or limits that can go to zeros, or any other number that could be improper. And if you have to use L'Hopital's rule to get the answer for this, that's what you do to get the answer. In this case, we're just going to say this is b squared plus 1 as limit as b goes off to infinity. There's an ln here. Okay. Minus ln of 0 plus 1, because right when x is 0, we go ahead and do that. And then we're going to go ahead and add this to the other side. So we have limit as a goes off to negative infinity. And then we have ln of 0 plus 1. And inside the log, that's going to be 0. Minus natural log of, we're going to go off to negative infinity. So we have a squared plus 1 inside the natural log. Okay. And it turns out that this guy goes off to infinity, and this guy goes off to infinity. There's not a whole lot we can do with this. Like, this is going to diverge. This guy is going to diverge. Once you have divergent things, and one of the things for math people that we are not very creative when it comes up to naming things. Okay? We have other people to name things for us. So when something diverges, it just means it doesn't converge. So if we're gonna go ahead and like integrate from 0 to infinity of like, sine x, then okay, yay, we just, or obviously cosine x. So when I integrate it, we'll just get sine x from 0 to infinity, which means, if I looked at the graph, it just goes on and on and on like this. It doesn't really settle down to any one particular value. Since this doesn't actually settle on a specific number, and say, well, what doesn't converge? Well, if it doesn't converge, then it diverges. Like, I don't want you to think that goes off to infinity. It just means that it doesn't settle. It doesn't come to one particular number. It just goes back and forth and oscillates forever and ever and ever. And we never actually get an answer for this thing. So in this case, these guys diverged. So we have this whole thing diverges. So E of x, right, my average for 1 over pi, 1 over 1 plus x squared, this diverges. Okay, and because this diverges, you're actually going to get a very similar kind of a problem or similar result for standard deviation and moment and for skew and everything else. So it's kind of a neat distribution in that it is a probability distribution, but it doesn't have a mean because the mean diverges. You don't get to do that. So it doesn't have a mean. We don't really know what that's going to be. Okay, so we can go ahead and look at that. Okay, so that's another flavor of problem. So far we have checking to see if a function or if something is a probability distribution. And then we have calculate the expected value. Okay, there's one more calculation we could do, and that's to get the median. Okay, and the median is just defined as this. We're going to put an m here to off to infinity of f of x dx, and this has to equal 1/2. That's what median means, is that it's the probability of this point is going to be 1/2. Or you could also write this as negative infinity up to m of f of x goes out to 1/2. Right, so that's what the median is, and we could go ahead and calculate that. Sometimes we could ask you, like, what is m for one of these things, and then figure out what that problem is going to be. I don't think the book has any of them in there for that. I think one of the other books from one of the other classes that we no longer teach did have problems like that, but I don't think yours does. So that's probably not a good one to put on the table for me. So let's see. There is yet a third flavor, okay, of problem. And this one, and I apologize for you guys because I didn't realize the book had a bunch of these things, and now I'm thinking about it, I should have, is that they're going to talk about the normal distribution. Now, the PDF, the probability density function for the normal distribution is f of x equals 1 over the square root of 2 pi sigma squared e to the negative x minus mu over 2 sigma squared. Delightful. There is no possible way that you're going to be calculating these probabilities with the tools that you have. Okay, if we really wanted to calculate probabilities with this thing, I mean, I guess, because I was looking at the book, like, well, you could use trapezoid rule, you could use Simpson's rule. Well, yeah, you could, but we all have better things to do. This is not a thing that, they've made tables for this particular function because it's so used. If you're electrical engineering someday, they kind of skinny all of this stuff off, and they just go ahead and use this function. Okay, they take out all the constants and don't worry about them. But e to the negative x squared, this is called the Gaussian. Should probably capitalize that for Gaussian. But you'll see that quite often. And the shape of this thing just looks something like this. Looks something like that. So it kind of looks like the Cauchy distribution, but these tails are a lot smaller. They're a lot thinner. One of the things you could do is kind of approximate what the probabilities are going to be. And if you take your intro to statistics class, you're going to learn empirical rule. Okay, and that says 68% of your data is within 1 standard deviation. Okay, 95% of your data is within 2 standard deviations. And then 99.7% is within 3 standard deviations. They stop counting after that because you've got almost, I mean, some books don't even use 99.7. They say almost all. Like, okay, good enough. So one of the problems that they gave us was like, okay, we're going to calculate an IQ score. Okay, and they want to know what's the probability. We're going to say, well, they're going to give you a preamble first. They have to. Okay. We're going to say something like IQ, okay, is normally distributed. A lot of things are normally distributed. That's why we like to study this particular distribution. Not everything is, but a lot of things are. Okay, so IQ is normally distributed, and they're going to tell us that the mean is going to be 100. Is it 100? Yes, mean should be 100, and the standard deviation is going to be 15. And they want to know, what is the probability that we're going to go between 85x and 115? There is no way I want you going through and looking at this and saying, well, we could integrate. No, we can't integrate this thing. This function does not have a very nice integral at all. It doesn't have one that you're going to write down. There is no way using the tools that you have up until Calc 3, certainly Calc 2, but up until Calc 3, there is no way for you to actually get a usable integral out of this, out of the Gaussian problem. Okay, there's no way you could plug something in and, well, I'll integrate this. No, you won't. Okay, there's no U substitution. If there was, that would be great. It would make everybody who's taking statistics slaves. It would make their lives a lot harder because they'd have to do an integral. But everybody who knows how to do integrals would make our lives a lot easier because we would be able to do this. You can't do this. Okay, you could do it with Simpson's rule. That takes a long time. There's some other techniques you could use to get this thing. You could also do it with tables. You could do it with other things. We're going to do it with a calculator, which is why I will never be asking you this kind of a problem on an exam because you physically cannot do this problem. Okay, so I know I kind of lied to you on problem number 2 from the last exam, and you didn't have any way of calculating this thing out. And again, I'm deeply sorry for that one, and I know that caused people a lot of frustration, and I'm very sorry that I did that to you. But this one, I know in advance, this can't happen. I do know that 100 minus 15 is 85. 100 plus 15 is 115. So I am expecting that my answer should be somewhere around 0.68. So what we're going to do is we're going to use the calculator to do these kinds of problems. And I urge you that if they have them in the book, to like, hey, figure this thing out. It's a normal distribution. Use the calculator. Okay, so what we're going to do, okay, so the way you do this thing is you go ahead and you're going to hit distribution. So second function, see it says yellow distribution there, and we're going to go to norm CDF. This is going to be the area under the curve. What the PDF is going to ask us, what that's going to calculate is they want to know what this value is. So they're going to get e to the negative x minus mu squared divided by 2 sigma squared, 1 over the square root of 2 sigma squared. They're going to calculate the value that's on the top here. That's what the PDF is going to tell us is this guy. We don't really care what the y value is for this function. What we want is the area under the curve up to a certain point or between 2 certain points. So we're going to go to the CDF, that stands for cumulative distribution, and that is where you are actually integrating. So the calculator actually has this functionality built into it. So we're going to go to norm CDF. Okay, we're going to go to that. And you just type in, it's norm CDF. Okay, it's a low number, a high number, mean, standard deviation, and then it'll pop out an answer for you. Okay, with all the calculus that you know, this thing will do it in seconds. So the first one I have is like, okay, we've got, what's the probability? It's between 85 and 115. So we're going to go ahead and get that. We have 85, use the comma key, 115. And then our mean is 100. And our standard deviation was 15. So we go ahead and calculate that. And we got not quite 0.68 because this is a rule of thumb kind of an idea. This is like if you needed to estimate the probability, that's what these rules are for. So estimating. If you actually wanted to calculate it to 4 decimal places, which is, by the way, that's the rule of thumb, is probabilities always go out to 4 decimal places. So 1, 2, 3, 4, we would say 0.6827. So 0.6827. So 68% is not too bad of a guess considering what we're dealing with for that. What if I wanted to figure out, okay, what's the probability that x is greater than, and pick a high IQ that you'd like to beat, 120. Okay, what's the probability that x is greater than 120? What we're going to do is we go back to norm distribution, so second function distribution. We're going to go to norm CDF, okay? And we're going to go 120 for my low number. Pick a high number relative to the numbers that we're dealing with, right? We have an average of 100 with a standard deviation of 15. So think, like, once you get beyond three standard deviations, it's the probability after that is minuscule. Like these things after 3, this is a very small area under the curve, and I'll pull a physics kind of a saying for you on this one. Like we ignore second order calculations or second order effects, avoid third order effects kind of a thing. These are just going to be really, really small numbers. So pick a large number relative to the fact that you have an average of 100 and a standard deviation of 15. So once I've gone to like 145, that's going to be pretty big. Well, I want to go say, my high number, we'll say, we'll go up to 1,000. Okay. If you take intro to statistics class, they're going to suggest you use 1e to the 99. So they're going to say this. They're going to say norm, dist, 120, 1e 99. So 1 times 10 to the 99. You're going to be, okay, out maybe in the 50th decimal place, maybe in the 500th decimal place, it'll change. But up to 5, 6, 7, 8 decimal places, 1,000 will be plenty. And then my mean of 100 and my standard deviation of 15, and we'll see what that gives us. And it's going to be a small number, okay? Because, well, it's not going to be that small because we're looking for bigger than 120. 115 is still within one standard deviation. So it's going to be more than two, it's going to be like more than one standard deviation, but not by a whole lot more. Okay, so we're looking at like 34-ish percentage kind of thing. So it'll be less than that. Here we go with 100. And then 15. Go ahead and do that. And 0.09. Okay, and that's what you would go ahead and write down for your answer for that one. Let me go ahead and show you. It's 0.0912. Okay, so 0.0912. And that would be your answer. And quite frankly, when they ask you these kinds of problems, when they preamble it with this is a normal distribution, I know they suggest, well, you could use substance rules. Like, yeah, you could, but that's going to take a lot of time for how much time did it take me to do this in the calculator? Like somebody already did that with Simpson's rule. They programmed it into the calculator to make it work like this. So we're going to use the fact that you live in the 21st century and take advantage of some of the technology that's offered to us to answer some of these questions, not the long way, but the short way to go ahead and do this. Like nobody would ever expect you to do this by hand anyway, ever. So we're not going to try to be a slave to like, well, let's go ahead and do it. No, we're not going to do this by hand. You have a lot of calculus to learn. We're not going to do this one by hand like this. Okay. And again, I will promise to you that no, we will never be putting a normal distribution problem on an exam and expecting you to get an answer somehow. Like that's not going to be the case for it. Okay, you could do it with other things. There's other options that you could have, but that is not going to be a question I'm going to ask you. So I hope that clears a little bit out for doing the probability section. And yeah, if that helps, great. And if I can do some example problems, I sure will. And but yeah, keep doing your homework, keep up all the good work, and I'll get the test graded. Thank you. Good night.